In the distant depths of the constellation Scutum, thousands of light years away from Earth, there exists a star so vast that it challenges the limits of human comprehension. It is known as UY Scuti. At first glance, it is described as the largest known star ever observed. But this description, while powerful, is not as simple as it seems. The story of UY Scuti did not begin with a dramatic discovery, but with careful observation. In the early 2010s, astronomers using interferometric measurements and spectroscopic analysis began refining its properties. By 2012, studies published through institutions such as the European Southern Observatory suggested that this star could have a radius over 1,700 times that of our Sun. If placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. To understand this scale, we must step away from intuition. The Sun itself is nearly 1.4 million kilometers across. Yet UY Scuti expands to a size so large that light would take hours to travel from one side to the other. It is not a solid object, but a diffuse glowing atmosphere of gas, constantly shifting and expanding. The boundary between the star and space is not clearly defined, and this is where the certainty begins to fade. Measuring a star at a distance of 5,000 to 10,000 light-years introduces unavoidable uncertainty. Even small errors in distance can dramatically change its calculated size. What we call the largest star may, in reality, be an estimate shaped by the limits of our instruments. This raises a critical question for modern astrophysics. Are we observing the true largest star in the universe, or simply the largest one we are currently capable of measuring? Because if UY Scuti is not the definitive answer, then something even larger may exist, hidden beyond our current reach, waiting to be discovered. In part 2, we step back from this cosmic giant and begin with something more familiar. To understand how large a star can truly become, we must first understand the rules that govern every star, including our own Sun. To understand how a star like UY Scuti can exist, we must begin with a paradox. The universe does not create giants first. It begins with stability. At the center of our solar system lies the Sun, a star nearly 1.4 million kilometers across. It contains more than 99% of all the mass in the solar system and has sustained nuclear fusion for over 4.5 billion years. By human standards, it is enormous, but in the context of the galaxy, it is unremarkable. This understanding took shape in the early 20th century. Around 1910, astronomers Einar Hertzsprung and Henry Norris Russell independently developed what is now known as the Hertzsprung-Russell diagram. This framework organized stars based on their temperature and luminosity, revealing a clear structure in stellar evolution. What this diagram showed was profound. Most stars exist in a phase known as the main sequence. In this stage, a star maintains a delicate balance. Gravity pulls inward, while nuclear fusion in the core pushes outward. This equilibrium, known as hydrostatic equilibrium, keeps the star stable for millions to billions of years. At first, this suggested that stars follow strict and predictable rules. Their size, brightness, and lifespan appeared tightly linked to their mass. Larger stars burned hotter and faster. Smaller stars remained dim but long-lived. The system seemed ordered, almost controlled, but hidden within this order was a critical transition. The main sequence is not permanent. As hydrogen in the core is gradually exhausted, the balance begins to fail. The core contracts, temperatures rise, and new layers of fusion ignite beyond the center. This is where the transformation begins. The outer layers of the star respond dramatically. They expand outward, growing larger and less dense. A once stable star begins to swell, moving away from the predictable structure defined by the Hertzsprung-Russell diagram. And it is within this transition that the path toward cosmic giants is formed. What follows is a deeper question. If stars can expand beyond their original size, what ultimately prevents them from growing without limit? The answer lies not in observation alone, but in the fundamental laws that govern pressure, radiation, and gravity. There is a limit to how large a star should be, not a visual limit, but a physical one, written into the laws of the universe itself. And for decades, astronomers believed they had already found it. By the late 20th century, astrophysical models suggested that no star could exceed roughly 150 times the mass of our Sun. Beyond this threshold, the energy produced by nuclear fusion would generate intense radiation pressure, strong enough to push matter away faster than gravity could hold it together. A star attempting to grow beyond this limit would effectively tear itself apart. This idea was not speculative. It was grounded in equations describing stellar structure, supported by simulations and consistent with the stars observed at the time. The universe, it seemed, enforced a strict upper boundary. Then came the observation that challenged it. In the early 2000s, using data from the Very Large Telescope operated by the European Southern Observatory, astronomers studied a dense star cluster known as R136 in the Large Magellanic Cloud. Within it, they identified an object now called R136-A1. Analysis of its luminosity and spectral characteristics suggested a mass reaching approximately 250 to 265 times that of the Sun. This was not a small deviation. It exceeded the theoretical limit by a significant margin. If the models were correct, this star should not exist in its current form. To explain this, scientists proposed an alternative pathway. Rather than forming directly from a collapsing cloud of gas, R136-A1 may have originated from the merger of multiple massive stars. In such collisions, the resulting object could temporarily exceed standard mass limits before shedding material through powerful stellar winds. This interpretation preserved the underlying physics, but it also revealed something deeper. The limits we define are not always absolute. They can be bypassed under extreme conditions. And yet, even this discovery introduced a new complication. R136-A1 is one of the most massive stars ever observed, but it is not the largest in size. Its radius, though immense, does not approach the scale of red supergiants like UY Scuti. This distinction forces a shift in perspective. Mass and size are not the same. A star can be extraordinarily heavy without being the largest object in space. The question begins to evolve. If the most massive star is not the largest, then what process allows some stars to expand far beyond all others? A star does not become enormous by gaining more mass. It becomes enormous by changing its structure. For much of its life, a star remains stable, fusing hydrogen in its core. But this stability is temporary. As the hydrogen fuel is gradually exhausted, the balance between gravity and fusion begins to shift. The core contracts under its own weight, while temperatures rise to extreme levels. This transition marks the beginning of a new phase in stellar evolution. By the mid-20th century, astrophysical models, supported by observations of evolved stars, revealed what happens next. Fusion does not stop. Instead, it moves outward. Hydrogen begins fusing in shells surrounding the core, while helium fusion ignites deeper within. This layered burning releases enormous amounts of energy, far greater than during the star's main sequence phase. The response is dramatic. The outer layers of the star expand outward, cooling as they do so. The star grows in size, sometimes hundreds of times larger than its original radius. Its surface temperature drops, giving it a deep red appearance. This is the birth of a red giant. What makes this transformation remarkable is that it is not driven by mass alone. A star only slightly more massive than the Sun can expand to hundreds of times its size. Observations of stars like Mira A, studied extensively through ground-based telescopes and long-term variability surveys, confirm this behavior. Its radius can extend over 300 times that of the Sun, despite having a similar mass. This challenges intuition. Size is no longer a simple measure of how much matter a star contains. It becomes a consequence of internal processes, of energy transport, and of structural instability. And the process does not stop here. For stars more massive than roughly 8 times the Sun, the expansion becomes even more extreme. They do not simply become giants, they become supergiants. These stars push the boundaries of scale further than anything seen before, growing to sizes that begin to rival entire planetary systems. This is the pathway that leads toward the largest stars in the universe. But as stars grow larger, they also become more unstable. Their outer layers begin to pulse, shed, and blur into surrounding space, making it increasingly difficult to define where the star truly ends. And this introduces a new challenge. If a star has no clear boundary, how can its size be measured with certainty? There are stars so large that if placed at the center of our solar system, they would consume the planets entirely. Not metaphorically, but physically, their outer layers extending beyond the orbits we consider stable. One of the most studied examples is Betelgeuse, a red supergiant located in the constellation Orion. By the early 21st century, observations from facilities such as the European Southern Observatory and NASA-supported telescopes estimated its radius to be more than 700 times that of the Sun. If positioned where our Sun is, its surface would stretch beyond the orbit of Mars, and under some estimates, even approach Jupiter. But Betelgeuse is not a solid sphere. It is a dynamic, unstable system. Its outer layers expand and contract in irregular cycles, driven by internal energy fluctuations. These pulsations can alter its apparent size over time, making precise measurement difficult. In 2019, Betelgeuse underwent an unexpected dimming event, observed globally by astronomers. Initially, this raised speculation about an imminent supernova. However, detailed analysis later revealed that the dimming was caused by a massive ejection of material, which cooled and formed a cloud of dust, temporarily obscuring the star. This event provided critical insight. It showed that these enormous stars are constantly losing mass, shedding vast quantities of gas into surrounding space. Their boundaries are not fixed. They are constantly changing. This instability introduces a fundamental problem. When a star expands to such extreme scales, its outer layers become so diffuse that the distinction between the star and the surrounding space begins to fade. This means that the concept of size itself becomes uncertain. What we measure as the radius of a supergiant is not a sharp edge, but a gradient, a transition from dense plasma to interstellar space. And yet, even Betelgeuse is not the largest known example. There exist stars that push this expansion even further, reaching sizes that challenge not just measurement, but the limits of stellar physics itself. To understand those objects, we must look beyond nearby examples and focus on the most extreme candidates ever identified. Beyond the familiar giants of our galaxy lies a star that redefines scale itself. Not through brightness, not through mass, but through sheer expansion. This is UY Scuti. Located in the constellation Scutum, thousands of light years from Earth, UY Scuti is classified as a red supergiant. Detailed studies conducted in the early 2010s, combining spectroscopic analysis and interferometric measurements, suggested that its radius could exceed 1,700 times that of the Sun. At this scale, light would take hours to travel from one side of the star to the other. To understand this, consider the solar system. If UY Scuti replaced our Sun, its outer atmosphere would extend beyond the orbit of Jupiter. Billions of suns could fit inside its volume. And yet, despite its immense size, it is not particularly hot. Its surface temperature is significantly lower than that of the Sun, giving it a deep red appearance. This is the paradox of the largest stars. They are not dense, blazing spheres, but vast, diffuse envelopes of gas. Their outer layers are so extended that they blur into surrounding space, making it difficult to define where the star truly ends. The measurements themselves carry uncertainty. UY Scuti lies between approximately 5,000 and 10,000 light-years away. Even small variations in this distance can significantly alter calculations of its radius. Observations from ground-based telescopes and stellar modelling provide estimates, not exact values. This introduces a critical limitation. The title of largest known star is not absolute. It depends on how we measure, where we observe from, and how we define the boundary of a star. Yet even with these uncertainties, UY Scuti represents the most extreme example currently identified. It sits at the edge of what stellar physics appears to allow. But there is a deeper constraint at play. Stars cannot expand indefinitely. At some point, internal processes begin to counteract this growth, imposing a boundary that even the largest stars cannot cross. To understand that boundary, we must turn to the physics that governs stellar stability at its most extreme limits. There is a boundary beyond which a star cannot grow, not because we fail to observe it, but because the laws of physics do not permit it. This boundary is known as the Hayashi limit. First described in the 1960s by Japanese astrophysicist Yoshiro Hayashi, this limit defines the maximum radius a star can achieve while remaining in hydrostatic equilibrium. It is not an arbitrary threshold. It emerges from the physics of convection, temperature and pressure within a star's outer layers. To understand this, we must look at what happens inside a red supergiant like UY Scuti. As the star expands, its surface cools. When the temperature drops below a critical point, the outer layers become fully convective. Energy is no longer transported efficiently through radiation, but instead through turbulent motion. At this stage, the structure of the star begins to destabilize. If it expands further, gravity can no longer support the extended envelope. The outer layers start to collapse inward, forcing the star to contract. In simple terms, the star reaches a natural boundary. It cannot grow larger without losing stability. This creates a hard constraint. No matter how much material a star contains, its size cannot exceed the limit defined by its mass and temperature. The universe allows enormous stars, but only up to a point. Observational data supports this. The largest known red supergiants, including UY Scuti and similar candidates, appear to cluster near this theoretical boundary. Their sizes are not random. They are confined within a narrow range that aligns with predictions from stellar models. This agreement between theory and observation is significant. It suggests that even the most extreme stars are still governed by well-understood physics, and yet there remains uncertainty. Some distant candidates, such as WOHG 64 in the Large Magellanic Cloud, show properties that are difficult to measure precisely. Dust, mass loss, and distance all obscure accurate estimation. It is possible that some stars may appear to exceed expected limits, not because they truly do, but because we cannot measure them with complete accuracy. This leaves us at a critical point. If the largest stars sit at the edge of a physical boundary, then the question is no longer how big a star can get. The question becomes whether we have already found that limit, or whether something just beyond it still remains hidden. To answer that, we must confront the limits of observation itself, where distance, resolution, and uncertainty begin to shape what we believe the universe contains. The greatest obstacle in finding the largest star is not distance alone, it is clarity. As we look deeper into space, stars do not appear as defined objects. Their light spreads, their edges blur, and their true size becomes increasingly difficult to determine. What we observe is not the star itself, but the radiation passing through layers of gas, dust, and expanding material. This limitation became evident in observations of WOHG 64, a red supergiant located in the Large Magellanic Cloud approximately 160,000 light-years from Earth. In the 2000s and early 2010s, data from observatories such as the European Southern Observatory suggested that this star might rival or even exceed the size of UY Scuti. But measuring WOHG 64 is not straightforward. The star is surrounded by a thick envelope of dust and expelled material, obscuring its true boundary. Its light is scattered and absorbed, making it difficult to determine where the star ends and its surrounding environment begins. This introduces a critical challenge in astrophysics. When observing extreme stars, we are not measuring solid surfaces. We are interpreting signals distorted by distance, temperature, and motion. Even small uncertainties in distance calculations can lead to large differences in estimated size. Modern techniques, including interferometry and spectral analysis, attempt to overcome these limitations. By analyzing how light spreads and shifts, astronomers can estimate stellar radii with increasing precision. But even these methods rely on models, assumptions, and indirect measurements. This means that the title of the largest star is not fixed. It is provisional, dependent on the quality of our observations and the limitations of our instruments. and this uncertainty carries deeper implications. If our measurements are constrained, then it is possible that larger stars exist beyond our current ability to detect them clearly. Not because they are rare, but because they are hidden within the noise of distant observation. This shifts the question once again. We are no longer asking how large a star can become. We are asking how much of the universe we are truly able to measure. And beyond that boundary of measurement lies a possibility that has yet to be confirmed. If stars can approach the limits of physics, could entire populations of extreme objects exist that we have only just begun to glimpse? The search for the largest star does not exist in isolation. Across the universe, a similar pattern is emerging. Observations are beginning to outpace the predictions of our models. In 2022, the James Webb Space Telescope began returning data from the earliest epochs of the universe. Among its discoveries were galaxies forming far earlier than expected, some observed less than 300 million years after the Big Bang. According to prior models, such structures should not have had enough time to grow and evolve to that level of complexity. This discovery was not marginal. Spectroscopic analysis confirmed extreme distances, placing these objects at redshifts greater than 10. Their brightness and chemical composition suggested rapid star formation and early enrichment with heavier elements. In simple terms, the universe was building complex structures faster than predicted. This matters because stars are not isolated systems, they are part of a larger cosmic process. The same physical laws that govern the formation of galaxies also influence the birth, growth, and limits of stars. If galaxies could form earlier and evolve faster than expected, then the environments that produce extreme stars may also be more efficient than our models suggest. This introduces a broader implication. The largest stars we observe today may not represent the true upper boundary of stellar size. They may simply reflect the limits of what our current observations have revealed. Across different scales, from individual stars to entire galaxies, the pattern is consistent. The universe does not always follow the timelines we expect. It often reaches extremes more quickly and more efficiently than our theories predict. This does not mean our models are incorrect. It means they are incomplete, and this incompleteness leaves room for possibility. If the universe can produce galaxies earlier than expected, and stars that approach theoretical limits, then it is reasonable to consider that even more extreme objects may exist beyond our current observational reach. The question is no longer whether such objects are possible. It is whether we have the tools to find them. Because as our instruments improve, each new observation has the potential to reveal something that reshapes our understanding of scale. And at the edge of that understanding lies a final question. What does it truly mean for something to be the largest in a universe that continues to expand beyond our expectations? The largest star in the universe is not a single object. It is a boundary. For decades, astronomy has searched for a definitive answer, a single star that could be named the largest with certainty. Observations of red supergiants like UY Scuti suggested that we had reached that limit. Theoretical work, from the Hertzsprung-Russell framework of the early 20th century to the Hayashi limit described in the 1960s, appeared to define the maximum scale a star could achieve, but each layer of understanding introduced a new complication. Mass and size do not align. Measurement is uncertain. Boundaries are not fixed. Even the most advanced observations rely on interpretation. This leads to a central realization. The largest star is not defined by a single measurement, but by a range of physical constraints. A star can grow only as large as its internal structure allows, balancing gravity, radiation, and convection. Beyond that, instability forces it to contract or shed its outer layers. In simple terms, the universe does not allow infinite growth. It allows extremes within limits, and yet those limits are not static. Modern instruments, such as the James Webb Space Telescope, have already shown that the universe can produce structures earlier and more efficiently than expected. Discoveries made since 2022 have challenged timelines, suggesting that complexity emerges faster than our models predict. If this applies to galaxies, it may also apply to stars. This does not mean that a star larger than UY Scuti must exist, but it means the possibility cannot be ruled out. The largest star we know may not be the largest that exists. It may simply be the largest we have been able to measure so far. This is the true meaning of the behemoth. It is not a single star, but the edge of our understanding, the point where observation meets limitation, where theory approaches its boundary, and where the universe begins to exceed our expectations. In a cosmos that continues to expand in both size and complexity, definitions remain temporary. Each discovery reshapes what we believe is possible, and somewhere beyond the reach of our current instruments, there may be objects that push these limits even further. Until we find them, the question remains open, not what is the largest star, but how far the universe is willing to go.